This is Surveying 1, Lecture 5, and the title of the lecture is Distance Corrections. More correctly, it's probably taping corrections, but some of these corrections are applicable to distances measured in other ways as well. So a fundamental equation when it comes to the kinds of corrections we're talking about is to correct for systematic errors in taping. And so the basic equation is that the corrected distance is equal to the measured distance plus sigma corrections, or when we usually read it, we'll say sum of the corrections, because that's what that capital letter, Greek letter sigma means. It means to sum them all up. Now, keep in mind that a measured distance, meaning whatever you measure with a tape, for example, whatever you measure for a tape with the tape between 2 points is rarely correct. There's always some kind of correction that needs to be applied to it. It may be that it's correct enough and you don't need to apply any corrections to it, but seldom is it actually correct at the outset. So there's always corrections that can be applied to it to make it a better value. And it all depends, as surveyors, for you to understand what the application of the result is to know whether you should be applying corrections and sometimes which corrections to apply, because some are more significant than the other. Keep in mind that the corrections can be positive or negative. So over here on sigma corrections, it may be that some of the corrections are positive, some of the corrections are negative, and there's actually more negative ones than positive ones, so that when you add them all together, that the net effect is to reduce the measured distance to give you a corrected distance that's smaller than the measured distance. Obviously, it can go the other way as well. And as I say here, this is really for all surveying. So here I've used the word distance, but really it's the true measurement, or the corrected value, the true value is equal to whatever you have observed plus the sum of the corrections, again, remembering that each correction can have a positive or a negative sign. So let's walk through some of the corrections that can be applied in the case of a tape. Now, why are we doing this? Again, you may have this question. For those of you, especially with some exposure to surveying, it's very common to measure distances with either GPS or an electronic distance meter, often expressed as EDM. So why are we talking about taping? Well, there's a couple of reasons. GPS and EDM are not very accurate for really short distances. Surveyors just ignore this and don't even realize the impact of those errors in their measurements. That's one. The other is that by talking about the various kinds of corrections that can be made with the tape, it develops more awareness in you as to the types of errors that are also existent in all the other technologies, so that you can better understand how to manage them. That is, how to evaluate their magnitude, determine if they are significant, apply them, and so forth. One of the most common things with many types of measurements is to somehow standardize your measuring tool. So they have these ribbons of steel that are constructed in a factory, and they're supposed to be 100 feet, 0.0000. You name the zeros. I would ask you to tell me how accurate you think these things can be. Well, they're usually built in a factory, so chances are temperatures are around room temperature, whatever that might be. So keep in mind that as steel heats up, it expands. As steel cools down, it contracts. So there is an impact. And so you can actually have, with variations in the room where the tape is being made, if they don't control it strictly, the tapes actually come out with different lengths. And so one of the things that we talk about is the calibration process for the incorrect length of the tape. And so the way you do this is you usually have two reference marks, and these two reference marks have been somehow measured with a lot more accuracy than you can with a normal steel tape. One of the most common things to do is to use what's called an INVAR or LOVAR tape. INVAR and LOVAR tapes are special steel alloys that do not change very much with temperature. And then they very carefully maintain tension and use special tools to have an extra stable measurement process to calibrate the tape. And it's very easy to measure then the distance between two reference points to 1/1000th of a foot. And I've even seen calibration lines that have been determined to 10,000th of a foot. Keep in mind, when it's 10,000th of a foot, even warming of the building and cooling of the building, meaning the expansion and contraction of steel and concrete in the building, could cause that baseline distance to vary. So very rarely is a calibration baseline that's calibrated to 10,000th of a foot standard for very long, meaning they're constantly recalibrating it. Now you can calibrate one of these tapes in what's called a fully supported condition, meaning it's laying flat on the floor or on the ground where these two reference marks are. Or it can be calibrated fully supported, which means in the field, you as surveyors in this class would be using plumb bobs, and they would use the same thing, but they might use supports, things that look like small stools or benches to support the tape, and maybe use weights and pulleys to apply a certain amount of tension so that it's very, very stable when they do the calibration. Typically, you try to use a tension on the tape that's likely to be the tension that you would use in the field so that you don't have to worry about any variations due to that. And of course, you would always measure the air temperature at which you are calibrating the steel tape. Now, this is a really important thing that also applies to other types of calibration. It's very common for surveyors to think that the way you measure the temperature of the tape is to go put the thermometer, especially if it's a thermometer, a mercury thermometer, the bulb, it just laid down on the ground next to the tape. That is never the case, except in very rare circumstances that you should be using to measure the temperature. What you do is you want to measure the temperature of the air in the shade. So you have to somehow get it shaded, get the bulb shaded so that the rays of the sun are not directly hitting the sensing part of the thermometer, because that can cause an artificially high reading. So that's another really important part. So I'm going to talk about how you would calibrate. Now, this is not something that we would typically do in all our classes. There are facilities for calibrating, but I want to make sure you understand how this is done, because the math behind it may be somewhat puzzling, and I want you to try to understand that there's really a very simple process here, and if you can get this down, then you will probably get all the other forms of correction for taping. So here's a calibration baseline. We have two marks that are very precisely set. And usually what happens, we set 2 points. They might be brass discs set in concrete, on a sidewalk, on the floor of a building, in the pavement of a road, or if it's a dirt or grassy area, you would probably have cylinders of concrete that are several feet long that are embedded in the earth, and the brass discs would be on the top of them, because you want these to be very stable. And then you would have holes punched into them to mark the very precise reference point. So what we do is we build the baselines first, then we go out with our INVAR tape and specialized equipment and calibrate how those two marks are, how far apart they are. So the first thing you need to realize is that rarely are these two marks exactly 100.000 feet apart. So you have to deal with that when you calibrate your tape. That's one of the first things you have to deal with. Keep in mind too, over time, that distance may change. So you periodically recalibrate your baseline. I remember one particular baseline that I used for about 10 years, and that over a 10-year period, it changed in length by about 4 thousandths of a foot. Why is that? It happened to be in a hallway. It was a concrete floor. There were probably cracks and settlement and several other things happening. And so over a period of time, they separated a little bit to be a little bit further apart than when I first did the check, did the actual calibration between the marks. So let's say we have 2 points that have been calibrated and they have been found to be 100.027 feet apart. What we now do is we stretch out the tape, and the way we do that typically is that we would hold 100 at one end and see where the divided foot would show up, the divided foot that's in the extra foot ahead or back of the 0 mark, and we get 100.035. And so the question is, what is the true length of the tape? Now when we ask this question, what do we really mean by what is the true length of the tape? The answer to that question is, what is the length of the tape when I stretch this thing out under the same conditions that it was calibrated? What do I get for the true length between the 0 and the 100-foot marks? That's what I mean by the true length of the tape. So it turns out in this particular case, with this data, you have 99.992 for the length between the 0 and the 100-foot marks. So one of the things that you have to look at is look at the numbers and figure out how did we arrive at this. One thing that I'll tell you right away that's kind of an indicator is if you subtract these two numbers, one from each other, the smaller from the bigger, you get 8 thousandths of a foot. And you notice that this number is 8 thousandths of a foot away from perfection. The question is which way to go. Is it 99.992 or is it 100.008? So let me show you a couple of ways you can analyze it. One is an approximate way, one is an actual exact answer. So here's those same two brass discs, and what I've done is done kind of a little bit of an analysis which doesn't exactly show you the way the tape is used. So what I'm saying is, let's assume that we align the tape so that the 0-foot mark is exactly lined up with one of the calibration points. Remember that we measured 100.035. So what that means is if we laid the tape out, the 100 mark would actually fall before the far calibration mark. And there would be a little bit longer to the actual point. And so one of the ways of looking at this is to say, okay, we have 100.027 from the 0-foot mark to this red line, which is the extension of where the other calibration point is. And we read 100.035. But we know that the actual distance between those 2 points, those 2 calibration points, is really 100.027. So if we want to know how far it is from the 0-foot mark to the 100-foot mark, we would simply subtract off this overage, and we read on the tape that it's 0.035. So if you subtract the 0.035 from 100.027, we get 99.92. Now, if you're really thinking hard about this, there are several assumptions made, and this is why it's an approximation. If you have a tape that's supposed to be 100 feet long, but it's not, then every mark on that tape is assumed to be proportionately longer or shorter from the next mark than it is supposed to be. So you have errors in the graduations themselves. But what we do here is we assume that because this is such a small distance, this 0.035 of overage, that we can assume it's close enough, at least at the resolution that we are measuring, to do this calculation. Now here's the exact solution. You create what's called a proportion, and I want you to start by looking at this equation where it says, so this is a proportion, so we say that the true length of the tape, meaning the distance from the 0 to the 100, divided by the measured length of the tape is equal to the true length of the baseline divided by the measured length of the baseline. And so for the true length of the tape, we leave it as that because that's what we're solving for. The measured length of the tape is what we read on the tape when we measure out a full 100 feet, and that is 100.00 feet. So that's why we have 100.00 here. The true length of the baseline is the data we were given, which is 100.027. The measured length on that baseline when we extended the tape between the 2 points was 100.035. Now if we had 100.027, obviously we know that the tape is exactly 100.000 between the 0 and the 100 marks. But we don't get that, so we know it's something other than that number. So what we do now is what's called cross multiplication. So your true length of the tape times 100.035 equals 100.027, and then we divide both sides of that equation by 100.035 to get that the true length of the tape is 99 and I just carried this out a number of places to get 99.9920028. Now, all this stuff here is ridiculous. It can't be that accurate, but that's how the proportion works out. And so typically you would round this out to 2, 3, or 4 places, depending on the care you had taken and the type of baseline it is and so forth. Now, on the cross multiplication, you may be able to see that it's even easier than what I just described, because if you took the 100.027, divided it by 100.035, and you simply multiply both sides of the equation by 100, that means that 100 on the left side cancels out, then you would get this same 99.992 as your answer. So that is how the calibration works, and this is something that you may want to spend some time thinking about. This is not the kind of thing where you watch it on the video once and you get it. Well, some of you will, but many of you will have to keep going back to this to try to visualize what's happening. And guess what? Even though this is hard to visualize for some of you, all the other corrections are actually much harder to visualize. Well, maybe not exactly. There are a couple that are pretty easy to visualize. But most corrections are pretty hard to visualize. So from this example, this tape is 0.008 feet too short whenever you lay out 100 feet. So if you measured 654.93 feet between 2 points, you really have measured something shorter, because we've already established that every 100 feet that we actually lay out on the ground is actually 99.992. So the way we calculate this, we compute these corrections. So you note here I have C sub L. So that's kind of a standard type of notation. C is always the correction, and then we put a little subscript number which is short for the name of the correction. And here I have used L, C sub L, which is because we're doing correction for length, meaning the incorrect length of the tape. So we say because we measured 654.93 in terms of tape lengths, that would be 6.55. Now it's really 6.5493, but one of the things you'll soon discover is that you don't need to have all those digits. You can round this to 6.55 and it'll be good enough. Times the 0.008 gives you a total error in this measurement of 0.052. So you see the true length of this measurement is 654.93 plus, remember the correction is always added, but this correction happens to be a negative correction, so plus a negative 0.052, which gives you 654.878. Now, one of the things we're going to talk about significant digits here when we get to a different part of the course, but you should have already read the chapter about this or read the material in the book about this in a particular chapter. Notice that I'd given you the original measurement as 654.93. Well, you can't make something out of nothing, so you really should be rounding this down to 654.88. Now, that's the easy part of the problem, in a sense, because one of the first things you have to do is when you are faced with a problem is, which problem am I solving for? Now, that may sound a little unusual. Let me explain. Let's say you've been asked to lay out exactly 400 feet to stake out a building foundation, or maybe 2 piers on a bridge, or something like that. If you've been asked to lay out a true 400 feet, then the problem is actually in reverse, because every time you measure 100 feet, you actually have less. So you calculate your error, C sub L is 4 times 0.008. So what you do here is you measure out 400.003 with this imperfect tape to get your true 400.00. So this is the exact opposite of the previous problem I worked in terms of applying the signs. And you go, well, is there a systematic way to understand this? Well, yes, there is. In the first problem I worked, we were solving for the corrected distance, knowing our measured distance, and we computed what the correction should be, and the correction turned out to be negative. If you're solving for the distance to be measured, given the true distance required, you need to rearrange the terms in this equation. So what I mean by this is, in this and exactly the previous problem, we were given that we want a corrected distance of 400 feet. We can compute what the corrections are, which was the 0.032, and this is what we're solving for. What distance do we physically measure out in the field to get our true 400? So if you look at it this way, and oh, by the way, this is a negative over here. So if you look at it this way and you're solving for the question mark, you see that if you rearrange using standard algebraic notation, that you get that the question mark is equal to 400 minus the sum of the corrections. So that would be 400 minus the minus 0.032, or you would add to give you the 400.03. So being very strict about how you handle your signs, how you handle the equation, how you understand which part of that problem in that equation you're solving for is important. So be aware of all of those things. All right, so let's talk about the impact of temperature variations. Temperature variations are probably the biggest source of error or corrections that surveyors need to apply when they're taping, or at least think about. And we'll talk later on, either in this lecture or near the end of the next lecture, how you kind of have to judge these things. But here's the equation that C sub t, so correction for temperature, is equal to Greek lowercase alpha times t minus t sub s times L. And as I say here, T is the temperature at which the measurement is made, and this particular equation is set up for degrees Fahrenheit. I said T sub x, it's actually T sub s, that's a typo. T sub S is the temperature at which the tape was standardized. So this would also be in degrees Fahrenheit. L is the total distance measured. Again, this is set up for feet. And alpha is the coefficient of expansion of steel. And this is something you can get from a handbook. Turns out to be 0.0000065. So that's 5 zeros, 65 per degree Fahrenheit. Now if you're working in the metric system, you would use degrees Celsius and alpha would be different. And depending on the textbooks you're looking at, you'll be able to easily figure out what alpha is. You can also make the conversion if you know how to convert between degrees Fahrenheit and degrees Celsius. This number here is something you should pay close attention to in the sense that you need to remember how many zeros. People sometimes get confused, and I always say 0.5065. Doesn't sound very elegant, but that's the best way for me to remember it. So here's an example. Tape is standardized at 65 degrees Fahrenheit. It's used at 95 degrees Fahrenheit. The length measured is 467.32. What is the corrected length? So the corrected length would be equal to the measured length of 467.32 plus the correction for C sub t. Now this is simply taking that very first equation I presented to you and writing it for this particular case. Now, if you are given a problem to solve in this class, or in the licensing exam, for example, and this is all the information you're given, then you can assume that you're not correcting for any other issues that might be involved. You know, it may be that this tape actually read 100.000 when it, between its 0 and 100 foot length, when it was calibrated at 65 degrees Fahrenheit. You notice, by the way, I said standardized here. Sometimes we say calibrated. There are other terms people might use, so just get used to the fact that different words might be used to express it. So the process is fairly simple. You calculate C sub t, and so that would be equal to alpha, I'm not going to write it here just to save some space, times t minus t sub s. So we used it at 95, it was standardized at 65, so that's 30 degrees, that's a positive number, times the 467.32. And here you use the whole distance L, not the number of tape lengths. So if we multiply this out, let me bring up my calculator. You have 0.0000065 times 30, 95 minus 65 is 30, times the 467.32, and we get 0.091. So this is a suggestion I have. Always carry out your corrections to one more decimal place for your intermediate values and then round down to whatever your result needs to be. I'll let you do the math, but the answer would be 467 plus 0.091 because this correction comes out to be positive. You notice that if the temperature had dropped, let's say we calibrated at 65 and measured at 35, then it would have been 35 minus 65 because it's always t minus t sub s, and we would have a negative value, and that would tell us right away that we needed to subtract the correction. Now let's talk about slope corrections. This will take us a little bit of time to wade through all these possibilities. The good thing is that with a modern calculator, you should become very adept at making slope corrections using different kinds of data to determine what the slope is. So what I said is, when you measure on a slope, you have to gather some information about the slope to be able to make the correction. Because what have you done? You measured a distance along the slope, and what you want to know is what is that horizontal distance. So this is the slope, this is the horizontal. And later on, we'll also be talking about a need to maybe calculate the vertical as well. So when you have a slope distance, you either know the difference in elevation between the endpoints of the tape or the entire line. So what do I mean by that? Sometimes you're measuring where the first 100 feet is measured like this, the second is flat, the third slopes down, but they're all different slopes. And so you have to apply the correction to each individual 100-foot measurement. But there are other times, especially if you're measuring along a road that's built at uniform slope, or a railroad track and things like that, that you have long patches of where the ground is very clean, unobstructed, and you can actually lay the tape on the ground fully supported. And so you might be able to measure hundreds, if not thousands of feet at the same slope. And that's why I say here, between the endpoints of the tape or the entire line. Or you might know the slope along which the line was measured. So you know that this particular road has a slope of 1.7%. Or you know the angle along which the line was measured. Angle meaning the angle usually with respect to the horizontal. So that would be this angle here. So let's go through those. So the first difference in elevation solution can be done using the Pythagorean theorem. So 500 feet were measured along the slope. The difference in elevation between the 2 points was 28 feet. What is the horizontal distance? So what you can do is say, okay, I know the slope distance is 500 feet. I know the vertical distance is 28 feet. What is the horizontal distance? So the Pythagorean theorem basically says that the square of the hypotenuse is equal to the sum of the squares of the other two sides. So we have that 500 squared equals the square root, oops, I'll put that square root in later, is equal to 28 squared plus h squared. Just to be clear here, because it looks like a z, that's h. So you can rearrange the terms and say that h squared equals 500 squared minus 28 squared, and that h is the square root of that number there. So you square 500, you square 28, you subtract that second number from the first number, and then you take the square root, and you would get what h is. So let's pull up the calculator again. So in this particular calculator, I can do it a bit faster. So 500, and I can square the number, and there's a direct function for doing that. right here. 500 squared is 250,000, and then 28 squared. So 28 squared is 784. I subtract that second number from the first number to get 249,216, and then I take the square root of it and I get 499 point, it's 2154, so I'm just going to call it 499.22. So in this particular case, you can figure out that C sub h, which would be the correction to reduce a slope distance to horizontal, is equal to 0.78 feet. That's the difference between the 500 and the 499.22. So that's one way to solve this using the Pythagorean theorem, and it's something you want to keep in mind. So let's say we have a different situation. It's similar to that sketch I drew at the bottom of 2 slides back, where we measured slope distances of 100 feet, but in each of those cases, and by the way, this is something that's commonly done in certain kinds of taping, where we actually pull out a level, which is the next topic we'll be discussing, measuring vertical distances, and we actually use a level to measure the vertical distance between the endpoints where we measured, where we placed the chaining pins in the ground, maybe we put a stake in the ground, whatever it is. And so these are the numbers that were used. This is not a very commonly used equation because this is an approximation, but I just wanted to point out that this is a fairly useful way to get a good handle on how significant the correction is, but as long as you're only measuring to the nearest hundredth of a foot or so, and it's not very steep, it's actually a fairly good equation. So the way you use it, it's v squared over 2s. So s is the slope distance, so we have 100, so it's always 200 in the denominator in this case, and we simply square these numbers. So in this case, it would be, let me bring up the calculator. So in this case, we would take 6 and we square it. So that's 36 divided by 200. And I get 0.18. So let me write that in. If you want 0.180. In the next case, it would be 18 squared over 2s. Can't do that one in my head. 324 divided by 200. 1.62. Quite a bit steeper, so a lot more shortening. Next one is 2.4 squared. .0288. So I'm going to round it to 9. This would be 3 squared, so 9 over 200. You probably can do that in your head. 0.045. And then finally, 9 squared, or 81 over 200. Or 0.405. I intentionally use 3 and 9 because 9 is the square of 3, and you see that even though we've gone 3 times the vertical distance, that the correction is not proportional. Here we have about half a tenth, and here we have 4/10. So keep that in mind, that this correction is not proportional. So I'll just do one of these. Now what you can't do is add this up and say we have 500 feet minus the sum of these. You can't do that. You have to apply it to each correction. And when you have a slope distance, remember the horizontal is always going to be smaller. So in this case, we would have 99.7, 0.82 and so forth. So I'll let you figure all these out, and then you can sum them to get the total horizontal distance for this series of 5 100-foot measurements that were measured with different slopes, but where the slopes were measured by determining the difference in elevation between the endpoints of that 100-foot line. All right. Then if you know the slope, so this should be fairly simple. If you know the slope, you have 500 feet on the slope, and you're told that this is a 5.7% slope. By the way, sometimes it's expressed this way. Just realize that as a pure number, this is actually 0.057. So as you move the decimal point over 2 places. What does a 5% slope mean? It means for every 100 feet on the horizontal that we go up 5.7 feet. This number, this 0.057, is how many feet we go up for every 1 foot. All right? So how do we use this? Well, keep in mind that what we're solving for is this, the horizontal distance. We really don't care about what this vertical is. So there's a couple of ways to do it. One is to do it by proportions. And to do it by proportions, what you'd have to do is use the Pythagorean theorem to first calculate the hypotenuse on what I call the 100-foot slope triangle. So let me do that. And that would be to take 100 squared and 5.7 squared, add them together, and then take the square root. So 5.7 squared and 100 squared, add them together, and then take the square root. I get 100.1623. Because I'm going to do proportions, I'll probably use all 4 digits. So 100.1623. Probably can get by with 3 digits, but I'm just going to go ahead and take 4. That way I don't have to think too much. And then what we say is, in this situation, we can say H is to 500 as 100 is to 100.1623. And so if we cross multiply, we come up with this equation that H is equal to 100 over the 100.1623 times 500. And if we do that math, 100 divided by 100.1623, and then multiply that by 500, you get 499 point, I'm going to call it 0.19. So that's one way to do it. There is another way to do it, and that's to recognize that the tangent of this angle, so let's call this angle A. Tangent of angle A is equal to 0.057. It is the slope number for that line. So what you can do is solve for A. Whoops, should have written here. Tangent of A equals 0.057. So you can solve for A by taking the inverse tangent. And then once you have A, let me just go ahead and do that. So I can do 0.057. I take the inverse tangent. So that's this tangent to the -1. And I get it's a 3.2623 degree angle. So A is equal to 3.2623 degrees. Now, in this particular case, you don't have to convert it to degrees, minutes, and seconds, which is often the bugaboo that many of you will have to go through in other parts of the course, because here, all you're doing is trying to calculate what h is. And so what you do is you look at this and you say, how do I solve for this? Well, if you remember SOHCAHTOA, I talked about that earlier, the cosine is equal to the adjacent over the hypotenuse. So now you take the cosine of this angle. So now I'm going to hit the cosine button and I get 0.9984. So 0.9984 is equal to h over 500, the adjacent over the hypotenuse. And if you multiply this out, you'll find you get the 499.99. So let me just multiply this by 500. I get 499.1897. I think that was slightly different, or maybe it was the same. I can't remember what my previous answer was, but you get the correct answer to the 3 decimal places. So that's how you solve that problem. You have a choice of doing it either way, and you should actually look at both situations, because what I find in this class is that people are often rusty on their trigonometry. You could say that doing it the first way I did it here is testing your skills in geometry and algebra, and the second way is testing your skills in trigonometry and algebra, and chances are you probably need testing in both of those areas. And finally, if you know the angle, well, the first thing you need to ask is which angle. So you should be getting some kind of information. And so in this case, let's say we have a 500-foot distance, and we're told that the angle with the horizontal, meaning this angle here, is 2.3 degrees. I intentionally kept it simple by keeping it at decimals. I could just as easily have said 2 degrees 18 minutes, which by the way happens to be 2.3. So you might think about how I did that in my head. And it's the same problem at this point as the trigonometric solution, because what you would say is that the cosine of 2.3 is equal to the horizontal distance, the horizontal distance divided by the hypotenuse, because h is the adjacent for the cosine, which would be the horizontal distance, and 500 would be the hypotenuse. And so you can solve this one. And so let me pull up the calculator. 2.3, take the cosine, multiply by 500, and we have our answer. That h is 499.60. And again, I'm rounding down to 2 places because that's implied right here in the problem statement. So you have to always look at that to figure out which way you're supposed to go. Now we have other corrections to talk about, but we're going to pause and pick up with another lecture to do that. So that'll be it for now, enough for you to chew on for a while.